We tend to think of weather as something that moves sideways. When we track a hurricane or a massive storm front, we see bands of clouds sweeping across the map, pushing horizontally from region to region. But that horizontal perspective creates a massive blind spot. Take a look at this temperature data overlay of the Earth's summer pole. For months, it sits in perpetual 24-hour sunlight. You would expect the atmosphere high above it to be baking. Instead, the data shows the summer polar mesosphere is the single coldest place on the planet. For decades, meteorologists tried to map out wind currents to explain this deep freeze. But relying exclusively on horizontal airflows, their climate models failed to simulate anything close to that extreme drop in temperature. The solution lies in the vertical dimension. These are internal gravity waves. To be clear, these have absolutely nothing to do with the gravitational waves in astrophysics that warp spacetime. These are purely fluid dynamics. Invisible, vertical ripples of air are the hidden engines driving the temperature and momentum of the entire atmosphere, linking the weather we experience on the ground all the way to the edge of space. The mechanism behind these vertical ripples is a constant tug-of-war between two basic forces. If a pocket of air is pushed upward, gravity pulls that dense air back down. But as it falls into heavier, lower layers, buoyancy pushes it back up. The air pocket ends up bouncing between these two forces. Physicists call the exact rate of this bouncing the Brunt-Väisälä frequency. It acts as the heartbeat of the atmosphere, setting the rhythm for how air oscillates up and down. Once an air parcel starts oscillating at this frequency, it knocks into the air above it, triggering a vertical domino effect that transfers energy from the troposphere directly into the thinnest layers of the sky. These vertical domino chains need a trigger. One of the most common happens when a fast-moving surface wind slams into a mountain range. The terrain physically forces the air column to ramp steeply upward, initiating an oscillation. Other times, the trigger is sudden and explosive. A massive volcanic eruption violently displaces millions of tons of air in seconds, generating enormous vertical ripples that shoot straight through the cloud deck. As the wave leaves the turbulent weather of the lower atmosphere and enters the stratosphere, it carries a vast amount of mechanical energy with it, the kinetic energy of moving air and the potential energy of displacement. If we track this in a data visualization, we see a mechanical trade-off. Because of the law of conservation of energy, the total energy of this wave must remain constant. But as the left side of this chart shows, the surrounding air density drops off exponentially. To compensate for pushing through thinner and thinner air, the wave's physical height, its amplitude, shown on the right, has to grow exponentially. What started as a modest bump over a mountain ridge stretches into a towering wall of thin air. The crests of the wave begin to warp and lean over themselves. The wave has become a precarious structure, ferrying immense kinetic energy from the solid ground directly into the fragile upper atmosphere.
Eventually, the wave reaches an altitude where it is simply too steep to hold its shape. Physicists call this the critical level. Just like a massive swell approaching a shallow beach, the atmospheric wave violently collapses and breaks apart. When it shatters, the wave irreversibly deposits its momentum into the surrounding high-altitude winds. This transfer of momentum acts as a powerful, localized force known as drag. This drag is intense enough to act like a physical wall against the massive planetary polar jets. It pushes back against these high-altitude winds, forcing them to decelerate and, in some cases, completely reverse direction. Alongside that massive transfer of momentum, the friction and turbulence of the breaking wave dump an enormous amount of heat, rewriting the temperature profile of the upper atmospheric layers. This drag on the jet streams forces a global circulation of air. As air is pushed upward into higher, lower pressure altitudes, it expands. Because air cools as it expands, this vertical pump creates the extreme adiabatic cooling that keeps the summer pole frozen despite the sunlight. To predict how planetary climates behave, scientists use global circulation models, or GCMs. These are massive mathematical simulations that wrap a planet in a rigid 3D grid, calculating temperature and wind changes inside each block. But there is a scaling flaw. To run on a supercomputer, the grid squares in these models are often hundreds of kilometers wide. Internal gravity waves are physically smaller than that. They slip entirely undetected between the lines of the simulation mesh. Because early models could not see this vertical transfer of energy and momentum, they were missing a crucial piece of the atmospheric math. Without gravity waves acting as an upper atmosphere brake, the simulated winds would spin out of control, causing the models to crash. To fix this, scientists developed a mathematical workaround called parameterization. Instead of trying to simulate the invisible high-frequency wave itself, the model calculates the specific amount of heat and drag the wave leaves behind when it breaks inside a grid square. Accounting for this subgrid data transformed GCMs from unstable simulations into tools capable of predicting climates on other worlds. On Venus, the atmosphere rotates up to 60 times faster than the planet itself. By applying the physics of momentum deposition, researchers found that gravity waves traveling in the direction of the rotation break and deposit their momentum as a push. This accelerates the upper cloud layers into their bizarre superrotation. On Mars, the atmosphere is mostly carbon dioxide. As gravity waves ripple up through the thin Martian air, their crests create temporary ultra-cold pockets. These localized temperature drops act as a flash freeze mechanism, sparking the sudden formation of carbon dioxide ice clouds high in the mesosphere. These Martian ripples are often born from extreme daily surface heating, which creates intense vertical convection columns, visible as massive dust devils, that punch upward and send waves radiating outward. The atmosphere functions as a vertically coupled system. Understanding the macroclimate of any world requires mapping these invisible ripples that link the surface to the stars.